Water, a remarkable molecule. We deal with water every day, and so we tend to take water for granted. Water is actually a very unusual substance. It has a low molar mass, 18 grams per mole, and yet it's a liquid instead of a gas at room temperature. If we look at a graph here of the boiling point of the substance as a function of the period in the periodic table, so here we've got H2O and H2S, H2Se, H2Te. Oxygen, sulfur, selenium, and tellurium, all in the same group in the periodic table. Oxygen's period 2, sulfur period 3, etc. And we graph their boiling points. If we did not have water graphed here, we would expect that its boiling point would follow this trend. That's not a very good line. It's harder to do than you might think. You would expect that water would fall around here somewhere, about minus 100 degrees Celsius. If water boiled at minus 100 degrees Celsius, then at 25 degrees Celsius, it would be a gas, right? And yet it's not. Its boiling point is way up here, 100 degrees in the positive instead of the negative. And the reason that this boiling point is so high is because the intermolecular forces that hold the molecules together are unusually high, unusually strong. Water is a polar molecule. It's got an oxygen-hydrogen bond. It experiences hydrogen bonding. And so because of the hydrogen bonding in water, the boiling point is much higher than we would predict just based on size. These are also polar molecules, but they do not do hydrogen bonding. So we see that there is a trend that the boiling point increases as the mass of the molecule increases for these similar compounds. Because water is very polar, it works as an excellent solvent. It can dissolve other polar substances, molecular substances, and many ionic compounds. It is the main solvent of living organisms. And that allows your body to transport nutrients and other compounds throughout your body and your blood. Life is impossible. Life as we know it is impossible without water. Most of the places where we find water, you find life. The way that water freezes is also very different. Most things, when they freeze, they become more dense. Water becomes less dense. You've maybe experienced this if you've ever put a full bottle of water in the freezer because it was going to be hot later and you wanted to freeze the water so it'd stay cold. What happens if you put a full water bottle in the freezer? It breaks, right? Because as the water freezes into ice, it expands. Its mass doesn't change, but its volume becomes larger. Its density becomes less. We see that ice is less dense than water because it floats, right? There's a couple ice cubes left in my water, right? They're floating on the top. They float because the density is less. The maximum density of water is actually at 4 degrees Celsius. So as you cool water down, it gets less dense and more and more dense, and until you get to 4 degrees, just above freezing point. And then when you get back below that, it starts to expand. It's really this reduced density of of ice. Oh my goodness, it's been a long week. The reduced density of ice has a lot of significance in the environment. If ice was more dense than water, as lakes froze, the ice would sink and the lake would actually freeze solid. I grew up in Minnesota, and fishing is a big deal there. If the lakes froze solid, all the fish would die. But what happens is that the ice on the surface floats and stays up there and acts as an insulating barrier and keeps the entire lake from freezing. It also causes, pipes to burst and some bad things to happen. Organisms that have a lot of water in them usually will not survive freezing. If you think of, do I have the picture? I don't have a picture. We get freezes around here, and some garden plants are susceptible to freezes, and you go out and there's the hostas, and they're just like wilted lettuce, right? Because they have a lot of water in their leaves, in their cells, and when the water in the cell freezes, it expands and the cell walls burst and the organism dies. Foods like lettuce do not freeze well. You can't preserve lettuce by freezing it because all the cells burst and it just turns into mush. You might as well just throw it away. There's a technique called flash freezing, and this is why things that you freeze at home may not be similar to things that you buy frozen at the grocery store. When they flash freeze, they do that so fast, they do it so fast that the water molecules can't line up with each other and expand. And so then the cell walls are preserved. So flash freezing can help. I think there's a picture back here. We need this picture. Pause. I need to put this picture in with the part about water. This is what happens with the water molecules when they freeze and become a solid. They're not just all randomly stacked together. They make this open crystalline structure where the hydrogen bonding between the molecules is maximized. And so then you have these almost tunnels, these open spaces in between. And that's why when water freezes, it arranges this way and it expands in volume. When you flash freeze it, when you freeze it very, very quickly, it can't do this, and it will freeze in an amorphous fashion, and the density will be less, and so it won't destroy the food. And there's the end of the chapter. So these are the things that you should review.
I have a question. You were saying that flash freezing, the density would not change?
Mm-hmm. Or not as much.
Right. My question is that the density would, it wouldn't increase and it wouldn't change. So there's no expansion, there's no creation of that amorphous form.
Well, the crystalline structure, when water freezes slowly, is not amorphous. It's crystalline, it's ordered. And that's what causes water to expand as it freezes.
Right.
If you freeze it very quickly and don't allow that to happen, then it'll have more of an amorphous shape and you won't get the spreading of the molecules. And so then the density stays the same, basically.